things before we go into this process for what the force concept model is about. And this is a follow-up on when we were talking about Newton's second law and what Newton's second law is about. When I talked about Newton's second law, I probably wrote something like this, that the acceleration an object experiences is proportional to the unbalanced forces that are acting on the object and the inertia of the object. And I probably wrote it out like that. Is that true? Then let's start right here, because this is an excellent place to begin. First, I want to be clear about this vector notation that we have here, because a lot of students don't fully appreciate this, and you need to a little bit to really understand what this is saying. A summation symbol means we're adding up all the things. And with the vector bar there, we're also saying that we're going to take into account the direction of each of those things. This, as a whole, can be hundreds of forces, but its direction is a combination of all of those forces. And the direction results in an acceleration. So the direction of the acceleration is the direction of the net force. And I know that that doesn't make a whole lot of sense to a bunch of you, so let me give you an idea of what I mean. Imagine that we have a boat in a river, and we're going to try and pull it by using ropes that are being held onto by people on the banks of the river. Now, they're pulling in different directions, right? So the two forces acting on the boat are certainly in different directions, but the boat is likely to accelerate in this direction. Does that make sense? That yellow arrow is the direction of the acceleration. It is also the direction of the net force. So even though no individual force is that way, the net force is in the direction of the acceleration. So when we talk about this bar on top, it is the vector direction of the net force. So there is a net force that is along the river due to the individual forces acting on the boat. So no individual force has to be in the direction of the acceleration, but the net force is in the direction of the acceleration. Next, we need to talk about inertia, and we really need to be very specific about what inertia is. It's hard to give a definition for inertia, but I'll do my best, but it's going to be circular logic. Inertia is an object's resistance to changes in motion. This whole phrase, changes in motion, could be replaced with the word acceleration. It's a ridiculous definition because that's what the whole second law is about. The idea that if you apply an unbalanced force, how much the object accelerates depends on how big the object is. So saying that, inertia is a measure of its resistance to changes in motion is kind of circular logic. But I can't really change the fact that there's no great definition of inertia. That was the whole point of what Newton's second law is about. He's trying to find a mathematical way to quantify this resistance to change. But keep in mind, inertia can be measured. You can measure an object's resistance to changes in motion. You can apply a known force to an object, measure its acceleration, and solve for inertia. You could do it this way. This is how you measure an astronaut's mass in a weightless environment. You put them on what's called a shake table, and it shakes them back and forth. It applies a known force and measures the acceleration of the astronaut. And that's how they determine the mass of the astronaut in orbit. It's a chair kind of thing, and it bounces them. But they have to maintain weight and have to maintain bone density. It's not easy to do. So to make sure that they're not losing any bone or muscle mass, they take their weight frequently. But that's just it. We use the word weight here all the time. We measure our size by measuring the force of gravity. But you don't have that if you're in a weightless environment. So they need to find a different way to measure somebody's mass. And that's the big thing. Inertia is a measure of mass. The more mass something has, the more difficult it is to change the object's motion. But mass is unique in that of all the intrinsic properties out there, mass is the only one that really has two different properties. There's the inertia part of mass, but there's also the gravity part of mass. Mass does create gravity and is acted on by the gravitational force. There was a time when scientists weren't sure that gravitational mass and inertial mass were the same thing because they had such different properties. Today, we accept them as being the same, that gravitational mass and inertial mass are the same thing. But it hasn't always been the case. In science, you have to kind of prove things and find evidence. And so far, the evidence bears out that inertial mass and gravitational mass are the same thing. But they do different things in nature. Lastly, we can rewrite all of this to focus on force. When we do, it helps us understand the units that we're going to be measuring force in. This side, of course, is the combination of all the forces, and it would have to be in the units of force. The right side says that the units of force would be the units of mass, kilograms, times the units of acceleration, which is meters per second squared. So this is our unit of force. It is a complex unit. You need to be able to recognize it. Some of our complex units have other names, and some of them don't. This one has another name, and the name that's been given is the Newton. I think you can probably figure out why. So we'll use a capital N as a symbol for this particular unit, but it's kilograms meters per second squared. I promise you on your next test is going to be pick the unit of force from a list, and it's going to have things like kilograms meters per second, kilograms meters squared per second, kilograms meters per second cubed. It's going to have all sorts of stuff in there. They're all going to look the same. The thing is, and I may not have made this clear, so let me make it clear right now. All of these are different units. They're all something in nature that we use on a regular basis in this class. Some of them have names you may know. Some of them don't have special names. But these are all different units in this class. And you'll have to be able to recognize all of them and know when to use them. So although we have a complex set of units, they all break down to kilograms, meters, and seconds at some point. So be ready, be prepared, because we're going to do a lot of stuff with units, and you're going to have to be able to be flexible. So if it were me, I would probably start an appendix that really talks about what the units are and start memorizing them, because it's not going to stay meters and seconds forever. It's going to start changing now. All right. With that, let's get to our point today. The force concept model. School is often a sequence of solving problems or answering questions. And of course, this class has been no different. But I think you should understand that the force concept model isn't about solving physics problems, not in the sense of these are textbook questions and you need to find the answer. The force concept model is about analysis. It's how you apply Newton's laws to analyze a situation. It has limits. It can only tell you the size of an individual force or the acceleration of the system. It can only tell you those two things. In fact, the force concept model doesn't even do that, really. The force concept model will generate relationships. It will generate equations. It'll make equations that are custom fit for your particular situation. And then from those equations, you can hopefully do some analysis to solve for an answer. But that's all it's going to do is generate a set of relationships. Now, some of these relationships are fixed, meaning there are some fixed relationships we're going to employ, some definitions that they themselves are relationships we're going to use. For example, one of them that's going to come up is the force of gravity, which we also call weight. It has a fixed relationship. We'll use a capital W for it, and it equals mg. Because weight would be the result of dropping something. Net force equals ma. In this case, a is the acceleration of gravity, so weight is equal to mg. Whenever we have to deal with something's weight, this is how we will calculate it until we have a better understanding of gravity. When we have a broader understanding of gravity, we will use something different for the force of gravity. But for today, weight's going to be mg. It's a fixed relationship that you can use almost every time for this chapter. But of course, this also tells you that if you know the acceleration on another planet or another moon, you can figure out what the weight of that object will be on the other planet or the other moon. An object's mass will stay the same between here and the moon, but its weight will change because weight is the force of gravity on the object. So this is why we say things weigh less on the moon. They're not smaller on the moon. Just the force of gravity is less on the moon. All right, so we're going to get into this a bit. And we're going to use the box on the table. Can you all see the box on the table? There's a box sitting on. There's a box on all of your tables, I think. So just pick one of the closest boxes. Just look at it. This is the most ridiculous example that there is. But the point of this example isn't about the box on the table. The point of this example is to give you a framework to solve questions. I'm going to write down a series of steps. You will not get this series of steps on your test. You will have to know how to apply this series of steps. And although it's going to feel like an infinite number of steps. It's not. It's going to be the same set of routines and steps every time. And once we are complete with our set of steps, and we've done 2 or 3 exercises, for the first week or so, I'll put them on this screen while we're working. So you'll have an outline of the set of steps, but you need to have a good, accurate representation of how to apply this. Now, you guys who had AP1 before, a lot of these steps are the same, but there's nuance in mechanics that isn't in AP Physics 1. We're going to start with the fact that every single problem begins by deciding whether we have a first law question or a second law question. Which of the 2 laws presides over your problem? I said from the beginning we are talking about a box on the table. So box, table. Box on the table. Now, answering whether it's a first or a second law problem isn't hard to do. You're really asking yourself, is the object accelerating or not? If you don't understand this, then put this in your notes explicitly. Accelerating means it's speeding up, slowing down, and or changing direction. It doesn't mean moving. An object can be moving and the net force is 0. It's only if the motion is changing that it's a second law problem. So something traveling at a constant speed not necessarily a first law problem. It has to be traveling at a constant speed and constant direction. Both of those have to be true for it to be a first law problem. Otherwise, it's a second law problem. Also, if you don't know the answer to that question, like if you don't know if it's a first or a second law problem, then you have to assume it's a second law problem. So when it comes to making this choice, is the object accelerating? If it is, it's second law. If it's not, it's first law. And if you don't know the answer, you have to assume second law until you can prove it's a first law. That's the order. Any question about that? Box on the table. Is it a first law problem or a second law problem? First law problem. I think the box is at rest with respect to the table. So its velocity is not changing. So we're going to say it's a first law problem. State it right at the beginning. Step 2. You're going to draw a free body diagram. Sometimes in your textbook it will be shortened to just FBD, but free body diagram. 20 to 25% of the AP Physics Mechanics exam is going to be on Newton's laws. I can guarantee you will be drawing a free body diagram for your exam. It's going to be there. And it may only be a simple one. It may be one where you have to draw it in great detail, where you're being careful to make sure the arrows you're drawing are of appropriate scale. Either way, you have to understand how this works. A free body diagram is it's just a diagram with arrows on it. That's all it is. But it's supposed to be a method to help you isolate the forces that are acting on your object. The first one we're going to draw here is completely ridiculous. It's so simple, it's not even worth doing. But remember, this isn't about this example. It's about applying a set of steps and a set of rules. So the free body diagram also is your way of evaluating the forces acting on your object. It's really a series of yes or no questions, but it starts by reducing your object to a dot. The idea is to take away the distractions of the problem. So anything that might be getting in the way of understanding the forces acting on the object, we reduce to a dot. We are only interested in the box. So the only thing we will have in our picture is going to be a dot representing the box. So everything disappears, and I only consider a single dot for the box. Next, you're going to draw an arrow from the dot pointed in the direction of the force. On your test, you had better use a ruler for this. Okay? For now, we're just going to be trying drawing some arrows. But on your test, these should be ruled lines, and the scale matters. Now, we have a list of forces behind me. Each force has a reason for why it's drawn. And so I'm going to go through each of them and help you understand whether it would apply in this problem or not apply in this problem, and give you what you would be looking for to see if it applies. The first one is the simplest one and will apply in every single problem you do. You are very likely to have to draw it, and that's going to be conservative forces. And in this class, the only conservative force that's going to come up is gravity. So you ask yourself, are there any conservative forces acting in the system? The answer will always be yes, and the answer is always going to be gravity. So you're going to draw an arrow downwards to represent the force of gravity acting on your object. Now, when you draw this arrow, drawing the arrow isn't enough. You are setting the scale for your drawing when you draw this arrow. The other arrows are probably going to respond to the size of the weight of the object, because the weight of the object tends to be an important factor in how things behave on the planet. So you're setting the scale for the rest of your diagram. Keep that in mind. The other arrows should be of a proportional size that makes sense for the first arrow that you draw. There are labels that are okay for this and labels that are not okay. These labels are acceptable labels. Capital W, capital F with a subscript W, capital F with a subscript G. Force of gravity, force of weight, or just weight. I will almost always use just the capital W. Almost always. In fact, I usually just do one-letter things for everything. It is unacceptable to use a capital G or a lowercase g. Those are already reserved for other things. You can't use them here. So these are a no-go, non-starters. Next, you're going to go through a list of contact forces. There's no guesswork here, although you will probably guess because you won't spend the time to memorize this. There's no guesswork. Contact forces only occur if the contact described is happening. If the contact described isn't happening, then these contact forces don't exist. They only exist under the circumstance of there being contact. For example, the first one is the normal force. This is a pushing force from a surface. A normal force is a pushing force from a surface. So, is your object in contact with a surface? Yeah, the table. Now, you can be in contact with more than one surface. If you're leaning against the wall, you might have the force against your feet from the floor and against your shoulder from the wall. Like right now, you're probably experiencing multiple normal forces. There's the chair on your butt, the chair on your back, the table on your arms. All of those would be considered normal forces acting on you. So when you talked about normal forces, it's based on the surfaces in contact. But the word normal here doesn't mean ordinary. It means perpendicular. A normal to a surface. So you don't even get to choose the direction of this force. The direction is based on the surface. When you draw in a normal force, you must draw it so that it is perpendicular to the surface in contact. So in the example we have here with the table, I'm going to draw an upward force because the table appears to be horizontal. So when I draw this, and be careful, I'm not going to draw it arbitrary, I don't see anything else that appears to be acting on the box. And I said from the beginning that I thought this was a first law problem. So I want to try and draw this force in such a way that it demonstrates balance. Because we said the net force equals 0. So when I said you have to draw these to scale, I mean you have to, if you say net force equals 0, your resulting diagram should support a net force that is balanced. And I say I see no cables acting on the box. I see nothing else pushing on the box. I think likely this is the only other force acting on the box, so I want to draw a normal force that shows balance. Acceptable labels, capital N, and force with a subscript of N. I will use capital N, which can be confusing since capital N is also reserved for newtons. But we usually don't have units inside our equations, so I think we'll be okay. Tension is next. Tensions are pulling forces. But there's got to be a cable, a string, your arm. If you grab something and pull, your arm is a conduit. The thing about tension forces is that tension forces are in the direction of the cable. So they're always a pulling force, but they can be in almost any angle or any direction. It's going to be in the direction of the cable. Does that make sense? But they're always a pulling force, so they occur in the direction of the cable away from the object. There's no tension force acting on the box, right? No cable connected to the box, therefore no tension forces acting on the box. Now there are other contact forces, but I'm actually going to group them into their own category and call them resistive forces. They are contact forces. They can only happen due to contact, but they behave a little differently, so there's reason enough to include them as their own category. There will be two that we will talk about. There's friction, and there's air resistance, also known as drag. We are not going to talk about drag or air resistance for quite a while. It's a complex force because it's proportional to velocity. So we're not going to talk about it very much until we've got a firm grasp of these other concepts. But friction we'll talk about straight out the gate. And here's where we are very different in this class than we were in AP Physics 1. You're going to be expected to be able to do some more complex problems dealing with friction because you're capable. So you AP 1 folks, we didn't do very much with friction last year, but you will do a lot with it this year. There are two types of friction. There's static and kinetic. Static is also known as starting, and kinetic is known as sliding. But friction is a force that prevents one surface from sliding past another. It prevents one surface from sliding past another. There's two kinds because static friction is a little complicated. It's a reactive force. But if you break static friction and an object begins to sliding, then sliding friction takes over. So sliding friction is a little different. It can only occur if the object's moving. Notice I didn't say if it's accelerating. Any motion, then there's going to be sliding friction if you're dealing with a frictional surface. So static friction, the object has to be at rest. So static friction only occurs if the object's at rest with respect to the surface. We're going to cover these in a little more detail later in the week. But for today, just understand we're going to use lowercase f, or you can use capital F with a lowercase f subscript. I will always use lowercase f. There are other forces in nature, like the buoyant force, which is the force an object experiences when it's surrounded by a fluid, and many others. This is it for today. In fact, this will be it for most of this unit because this is actually going to be quite a bit. This will be enough. So when you've made it to the end of this list and you've drawn all the arrows that you believe act in the problem, you have completed a free body diagram. The diagram itself is just the arrows with the dot. It's what we do with it that matters next. So after you've drawn a free body diagram, you're going to progress in our series of steps. We're ready to go? If you're asked to draw a free body diagram, this is where you stop. But ultimately, most of the time, you will have to use your free body diagram to continue to observe or analyze the problem. You may have to draw other arrows or draw in some trig and stuff like that. You may need a second diagram for that if you're being graded on your free body diagram. So often on a test, there will be a blank that says, draw your free body diagram here and nothing else. They mean it. Don't draw anything else in there. But we're going to continue. There's stuff that we have to do to this diagram. Everybody okay? All right, I'm erasing all the stuff that's in green. You guys got it down? Because drawing a free body diagram is its own set of steps on its own. So, step 3. You have to choose a coordinate system. You're going to superimpose a coordinate system over the top of your diagram. This is basically you choosing what direction you're going to call X and what direction you're going to call Y. There are priorities in this choice, and the priorities are in this order. The first priority is match the direction of the acceleration. If your object is accelerating, you want to point X or Y in the direction of the acceleration. If you don't, you will have so many more problems down the road. So if you want to make this as easy as possible, always match one of your directions with the direction of the acceleration. Your next priority is to line it up with as many forces as possible. The more forces you line it up with, the less work you have to do. So when I say create a coordinate system, I'm serious. You're going to take X and Y. And you're going to place it over your object. And you can choose to turn it however you want, but you want to line it up so that it lines up with the most number of forces. And this problem is kind of ridiculous. So the forces are all in one dimension. But once you do that, you are also deciding what direction will be positive and negative for every part of your problem. Right? You're going to line up a coordinate system and decide what direction you're going to call positive for the X and what direction you're going to call positive for the Y. Once you've done that, you're now in a position to apply Newton's laws. We started that all the way at the beginning, but now, because we have two dimensions, you take your Newton's law and you break it up into the net force in the x direction and the net force in the y direction. If you had a second law problem, one of these gets MA. If it's a first law problem, they both get 0. And this isn't an equation, it's a set of instructions. It says, take all the forces, add them up, taking into account their direction, and set that equal to 0. For the problem I have here at hand, I would have normal minus weight. Normal minus weight equals 0. Right? There's only 2 arrows. I chose to make the upward direction positive, so normal's positive and weight's negative. Add up all the forces, taking into account their direction, and set it equal to 0.